Engineering 305, Chapter 5, Sections 4 and 5, Statically Indeterminate Axial Loading. The course learning objectives that apply here are to be number 10 still, which we did last time, but we're still working on that. Calculate the deflection of a material subjected to axial loading, and the material can have varying cross-section properties or loads, and also to evaluate structures under statically indeterminate loading. The equations that apply from the study guide are the same two that we had in the last section. That is the axial loading deflection equation, delta is equal to PL over EA, AE, right? PL over AE, but that's okay, it's okay. And then this total deflection for wedding cake still applies, and we're also going to go back and use thermal strains, but we rewrite that in maybe a different way. And in fact, we're going to find out that we no longer can just apply some of the simple things that we've been doing. We're going to have to start creating our own equations, start including geometry, and start thinking bigger about our solutions. So we've got some different forms, but we're going to continue to introduce different forms of equations, or you're going to introduce different forms. You'll have to determine your own equations. So the first question we should be asking is, what is statically indeterminate? And statically indeterminate really means that you can no longer solve for forces based solely on the equations of static equilibrium. That is, if we look at this example 5.9, which is one of the ones that we'll be doing, we put a load out on the end of 150 kilonewtons, and if link B is made out of rubber and it's soft, that's what I mean by rubber, that it's something that's soft and can move. It's made out of that same Professor Hahn TheraBand stuff, that green material that I brought into class. If item A is made out of steel, link A is made out of steel, and it's rigid, it doesn't move at all, then you would very quickly determine that all of the weight is counteracted, all of the weight that's applied at D is counteracted at A, or with link A, and the force, and we can figure out then what that force is, because we just have to do a teeter-totter equation basically, or a seesaw, or a sum of the moments about C, and we can quickly figure out what the load is in A, because B doesn't support any of the load. Well, that's not really the situation, right? That A is not infinitely rigid and B is not really, really soft. It could be the other way around. It could be B is rigid and A is soft. Or it could be somewhere in between. And so we now are approaching situations where we don't know what the forces are because we don't know what the stiffnesses are. If you don't know what the forces are, we're not going to be in a position to determine when things will fail. So we have to go back and look at how stiff or how soft things are in order to get an idea of whether they're going to fail or not. So you're going to wind up needing to use or find additional equations that will allow you to set up a system of equations that you can solve. We are typically going to step into a situation where if we just apply the equilibrium equations, sum of the forces equals 0, sum of the moments equals 0. We're going to be at least one equation, maybe two equations short of a system that we can solve. And you'll see that as we work the example problems. These problems take on many different forms. They take on what we saw on the previous slide with this arm that's loading on two different things. We're also going to see in section 5, this is section 4, or this is really the combination of 4 and 5. In section 5, we start saying, well, there's temperature is acting on things, and temperature makes things move, but other things don't allow it to move. And how do those things work together? So, and I'm going to say, unfortunately, this is really best learned through examples and doing problems. So, and these are hard problems and they're longer problems because the systems are bigger. They're no longer 3 equations to find some of the forces, some of the forces in X, some of the forces in Y, and some of the moments. We now need to add deflection equations in, that our deflection is equal to PL over AE. And now we need to look at the deflection of this part of the problem is equal to or is in a ratio with this other part of the problem is. And we also, in order to make these problems, we come up with some really interesting assumptions. but that's the way these come about. And so I really think we need to dig in and do examples. So, and that's what I plan on doing. So my next presentation, I'm going to start working example problem 5.7. After that, I'll follow it up with example 5.8, then I'll do 5.9. Then we're going to go into the next section, section 5, and we'll start doing a couple more example problems there. I will say this, I think that this topic of statically indeterminate is a very challenging topic. Students, while the equations are simple-ish, we've got these, a couple 5 variable equations. You have to be creative and come up with other equations from your past, from high school geometry, from other areas, in order to close the loop and get enough equations to create a system that can be solved. So this, because of that creativity, this is challenging material. And I'm sure there are going to be some of you that'll like this, that'll jump right into this and do well. But overall, from experience, I know this is an area where we face some battles. So prepare for those and come in with a positive attitude. So see you in class, see you at the next example problems. Be well. Wrong button.